Swayam Prabha. Digital India. Educated India.
Good morning, everybody. Today we'll start with some brief exercises based on whatever we have done so far. So the first question is, we derived that the pressure can be written, the acoustic pressure can be written in terms of a function f, which is f of x plus ct, and another function g, which is of function of x minus ct, and given this, derive the following expression. That acoustic velocity can also be written in terms of f and g, but it's 1 over rho c times f minus g. Please work this out. We have almost done this exercise in last class in another form. So this is the first exercise, and I wish to explain what is meant by acoustic velocity. There was a question in last class as to what is the difference between acoustic velocity and the speed of the wave, or the speed of sound, which we denote as c, which is square root of dou p by dou rho at constant entropy. So when you think of a fluid, and if you think of a little fluid element, the fluid element gets displaced, and in this displacement it also has a velocity, and so you think of this little fluid particle moving, and it is the velocity of the small particle that is we refer to as acoustic velocity. It's also called particle velocity. The speed of sound c, which is square root of dou p by dou rho at constant entropy, that is the speed with which the wave itself travels. So that is the pattern is traveling with that speed. It's also called the phase speed. Now if you, to give an analogy, let's say we are standing in a line to take a movie ticket or something, and somebody pushes from the back, and you move a little bit, but you push the guy in front a little bit, and he pushes the person in front a little bit, and eventually even the person at the front of the line gets the push. And so although you are not physically moving, you moved only a few centimeters, but the wave itself moved several meters, and it is the speed at which this push travels, not the person's travel. It's the speed at which the push travels. Push is some kind of stress wave or something. So that speed would be analogous to our speed of sound, and the speed at which, or the velocity at which you move forward when you get a push, that would be analogous to the particle velocity or the acoustic velocity. I presume this is clear. So there were questions about what happens when the properties of the medium are non-uniform, and we had derived this classical wave equation under a lot of assumptions. There were lots of assumptions involved in deriving this. We said that the flow was not there, it was a quiescent medium, and temperature, density, pressure, the mean values of temperature, density and pressure were constant, and so on. We had to make a lot of assumptions because the equations get very complex, and also, as I mentioned, in the presence of flow, separating the acoustic wave from a vorticity wave and entropy wave is not and the wave from the base flow itself is not a trivial thing. So to keep things simple, we made these assumptions, and we derived this wave equation 1 over c squared dou squared p prime over dou t squared equal to dou squared p prime by dou x squared. Now let's try to relax these assumptions. So we had done this homework already, that we derived the equations for motion, or I presume we have done this already, the quasi-only equations for continuity, momentum and energy, and you can use this these expressions, these partial differential equations, and derive a wave equation for homogeneous medium. Homogeneous medium here would imply a non-uniform temperature or non-uniform density. Let us still keep the assumption that there is no base flow, that is, it's a quiescent medium, and relaxing this assumption that temperature is constant and density is constant, we can actually derive a wave equation. We still say that the mean velocity is 0, and hence the mean pressure is constant. This simplifies matters a lot, and now you can manipulate the governing equations and derive these two equations of the top equation is the wave equation in terms of the acoustic pressure, and the bottom equation is the wave equation in terms of the acoustic velocity. Please derive these two things, and I wish to note that the wave equation for acoustic pressure and the acoustic velocity now look different from each other. If you think of the classical wave equation, we saw that the wave equation for pressure was exactly identical to the wave equation for velocity, except that we had the same operator. You can replace the pressure P prime with the velocity U prime. But now you can see that although the second derivative terms are same, the first derivative terms are not identical in the operator for either equation. So please do this problem at home, and yeah, it will be a very interesting exercise. It is quite simple to do this. Now the last part is, can you find solution to these equations? Now if you go back and look at these equations, they are partial differential equations. To get a solution, a generalized solution of kind of the form f of x plus ct, g of x minus ct may not be so easy. It may be possible, and if you do it, you can surely get famous. I have derived solutions for this equation in harmonic domain. That is, you say that the p prime goes like p hat e power I omega t, and then you can try to reduce the equations, the partial differential equation, into ordinary differential equations, and then you can see if this ordinary differential equation is of the class of some of the existing differential equation. For example, to give you a hint, if the temperature is varying as a linear function, sort of the form T naught plus mx, then you would get you can reduce the ordinary differential equation to a Bessel's differential equation, and you can actually get the solutions in terms of the Bessel function. So please work out these problems, and now so now let us try to look at standing waves. In the last class, what we did was we looked at travelling waves, and we wrote the solutions for the travelling waves. Now we will try to derive solutions for the for standing waves. So let us start with what is called a quarter wave tube. So this is a tube which has one end open and another end closed. So let us say this is x equal to 0, and this is x equal to L, and this side is closed and this side is open, and we wish to solve for the wave field inside the stack. That is the idea. And you can actually see that this is similar to the some of the exercises you would have done in high school laboratories, where you took a tube and immersed it in water, and then you try to measure the length of the tube, and then you used a tuning fork to determine the resonant frequencies and so on. It also has more profound uses and implications. For example, we can model even with this problem a geometry as complicated as a solid rocket motor, because there you have both sides closed. So this is open on one side, closed on the other side. If you keep both sides closed, then we can actually get the geometry, the acoustic configuration very similar to that of a solid rocket motor, except that there is a nozzle which is very complicated, but the nozzle surprisingly behaves very close to a closed end. So solving this problem will certainly help in getting an understanding of more difficult problems. So what we first need to do is to write the boundary conditions. The way you solve any differential equation is to write the boundary conditions, and then we also with the boundary conditions we try to solve for the equations. So let us start solving this problem. We will start with the wave equation itself. So we make this ansatz that p prime equal to p hat of x e power I omega t. So if you substitute this over here, what I would get is 1 over c squared I omega squared, this would be so we can cancel e power I omega t on both sides, and I omega squared would be I squared is minus 1, so we can it's enough to write this as d squared because now it's a full derivative. Is this okay? Any mistakes? If there are any mistakes, please point out. This is the Helmholtz equation. We can rewrite omega over c as k. So we can indeed rewrite this equation as d square. I think from now on I would not write this dependence on x explicitly. I guess by now we are clear that p hat depends on x. And so this is the equation that we need to solve, and let us now think about what are the boundary conditions. So the boundary conditions are, we said that this end is closed and the other end is open. So what would a closed end mean in terms of boundary condition? When you have a closed end or a rigid end means something is rigid, that means it does not move. So we say that the velocity is 0, that is the boundary condition. And if you have, so let us write this down, at x equal to 0, u prime of 0 equal to 0. Now at what is the boundary condition at x equal to L? The yeah, why is p prime equal to 0? Because yeah, at the open end the end is exposed to the atmosphere, so the pressure is equal to the atmospheric pressure. So p prime is the pressure minus the base pressure, so p prime minus p bar, sorry, p prime is p minus p bar, and p is now equal to p bar, so p prime is 0. So these are our two boundary conditions. Now we need to write an expression for acoustic velocity before we proceed to evaluate this. So so we can use the linearized momentum equation, du prime by dt equal to minus 1 over rho bar dp prime by dx, and if you now substitute this ansatz, we said that p prime is p hat of x e power I omega t, and we also make an ansatz u prime equal to u hat of x e power I omega t. So let us box this here, and so when you differentiate e power I omega t, you get I omega out. And e power I omega t on both sides will cancel, so u hat equal to minus 1 over I omega rho bar So let us now try to write the solution for this differential equation. What would be the solution for this differential equation?
P cap a into e power of ikx plus b into a power of minus ikx.
Okay. So let us write that. So this is the solution, and before we proceed to actually solve the problem, let us take a look at this equation and we will try to interpret in terms of f and g, so that way we understand what is going on. So P prime would be P hat e power I omega t, so I multiply this by I omega t, so a e power I k x plus b e power minus I k x times e power I omega t, which I can rewrite it as a e power I times k x plus omega t plus b e power I times omega t minus k x. At this instant it is probably clear which is the left running wave and which corresponds to the right running wave. Which is the left running wave? Okay, let us take a look at it. So this would be this can so this is the left running wave, let us say of the form g of x plus ct, and this would be the right running wave of the form f of x minus ct. So what would be velocity? So velocity would be you use this expression for acoustic pressure on this equation for acoustic velocity. So let us do that. So u hat equal to minus 1 over I omega rho times dp by dx, so that will be ik will come out, ik, and there will be a u power ikx plus b e power minus ikx. So we can replace omega as k over c, so this in turn becomes, so the k's can cancel, rho c comes to the top, so this will indeed be minus 1 over rho bar c. I made a mistake, there should be a minus sign here. This okay? Now if you multiply this u hat by e power I omega t, we can get the expression for velocity in the time domain, and then we can see how the waves, left running and right running waves, are moving. So I am going to erase here. So this is the, what wave is this? Left running wave. And this is the right running wave, and we can see that the right running wave has a positive sign in the front. That is understandable because if you think of a compression wave, that is the pressure going up and moving to the right, the the fluid particle will move behind the wave but along with the wave. So that means there should be a plus sign because your particle is going towards the positive x axis. But if you are looking at a left running wave, and if you think of a compression wave moving to the left, the particle will also move along with it, behind it, to the left. So negative x axis is the direction of the particle, so that is why a minus sign is coming. So this is in congruence with our understanding, our intuitive understanding. So this having done this, we can actually proceed to implement our boundary condition. So this harmonic domain and time domain approaches both are very consistent with each other, as you saw. It is just that in harmonic domain it is quite easy to solve for the equations. So we say that velocity is 0, so that would mean that u at 0 equal to 0, and our expression for velocity was here is the expression for velocity. So we can say that e power I times 0 is e power 0, which is 1. So you will get a minus b equal to 0. So this would mean that a equal to b. So now we can rewrite the expression for pressure amplitude as a e power ikx plus b e power minus ikx, and we can replace this b with a. So this can be written as a times e power ikx plus e power minus ikx. Now what I will do is I will multiply and divide by 2 for convenience. So what is this expression? Cos kx. So this would be 2a cos kx p hat. So we got a nice simple formula for p hat. So now the second boundary, okay, I will wait. Any questions here? So the second boundary condition says that p hat of L equal to 0. So p hat of L would be 2a cos kl equal to 0, or alternately if a is not 0, then you should get cos kl is 0, and this is now an eigenvalue problem because there are only certain values of k which will actually make this relation satisfied. And for example, when is cos of some function going to 0? Huh? Yeah, so you 90 degrees, 270 degree and so on. So kl equal to pi over 2 would be the first solution. So k is 2 pi f over c times L equal to pi over 2, or f equal to well, let me f equal to c over 4L. This is okay? So now it is probably clear why this tube was called quarter wave tube, because you will have 1/4 of the wavelength within the tube. So we can see that L, which is the tube length, is C by 4f, which is C by f is lambda, so it's lambda by 4. So one length of the tube has 1/4 of the wavelength, hence it is called the quarter wavelength. Now we can get a general solution, so we can say that KL equal to 2n plus 1 into pi over 2, right. So K is 2 pi f over C. So therefore we can get a general expression for f as 2n plus 1 over 4 times C over L. I hope this is right, please check yourself. So this is the general expression for frequency. So n equal to 1, okay, n equal to 0 gives f equal to C over 4L, n equal to 1 gives f equal to C over 3C over 4L, and then you have 5C over 4L and so on. So the natural frequencies of this tube are given by C over 4L, 3C over 4L, 5C over 4L and so on. So these such a problem is called eigenvalue problem, because only for certain unique values of this parameter k you get solutions for the differential equation. So eigenvalue, eigen is a term from German which means one's own or unique. So only for these unique frequencies you get solution. So that would be the general mathematical term for these natural frequencies. They are called eigenvalues. It's one word, eigenvalues or eigen frequencies. Now let us consider a tube which is closed at both ends. So closed and closed. So the boundary condition would be u of 0 equal to 0, and here will be so can you try to work this out? I'll pause for 2 minutes to see if we can work it out, and then I'll do it. So our expression for acoustic velocity was u hat equal to minus 1 over I omega rho times So u hat of 0 would be e power 0 would be 1, so that will go like equal to 0. That means this a equal to b. So we can write u hat equal to minus 1 over rho c times a e power I k x, I will take the a out, minus e power minus I k x. And if I multiply and divide by 2i here and 2i here, I would get this would be 2i times minus a over rho c into what is this formula? Sin kx. Sin kx. So can we now proceed to determine what would be the eigenfrequencies? So we should get sin k equal to 0, and let us look when sin k will be 0 first, and when is the first root of sin k equal to 0 comes? K equal to, no, the next one, that is too trivial, huh? Pi. So kl equal to pi, k is 2 pi f over c, l equal to pi, or f is equal to c over 2l, and the general formula would be, yeah, f equal to nc over 2l. So our eigen frequencies or the natural frequencies are c by 2l, c by 2c by 2l, which is c by l, and so on and so forth. This okay? So let us try to work out a problem. Consider a solid rocket motor like a booster. Let us think about the PSLV. So the typical length of PSLV is of the order of PS1 motor is of the order of 20 meter approximately. So let us take it a round number, 20 meter long, and what would be the speed of sound? Temperature, what is the temperature? 3450 actually. T bar is almost constant most of the tube, equal to 50 Kelvin. I think 2500 would be the temperature you get if you burn methane or something, but this would be much more energetic material. I think if you can use gamma equal to 1.2, anybody has a calculator? Can you find out what is the speed of sound? What would be this? $1,095. So we can round it off to 1000 meter, per second. So let us say c is 1000 meter per second. So what would be the natural frequency? C over 2L, right? So C is 1000 divided by 2 into 20. So this would be 25 hertz. The actual this motor is a fairly stable motor. Any motor will have some level of oscillations, but this motor has been working very nicely. But they put pressure transducers and found that the frequencies which they see, the amplitude is very small, but you still see natural frequency in terms of small oscillations. The frequencies is of the order of 28 hertz, so we are pretty close with our really crude calculation. Yeah. Any questions? Yes, Piyush. Yeah.
Can we just resolve that differential equation by using the boundary condition as pressure at
Pressure. So there is in general you have to write a boundary condition in terms of the admittance or the impedance. Which is given by P prime over U prime, and there are formulas for this in terms of the, which is a function of the nozzle exit Mach number. So if we can use there is a formula given by Zinn on this, and if you can use that, and then you can get a better estimate for the natural frequency. So but it is very close to a hard end. Not although the nozzle is open, you think, but it's what I mean by closed end is most of the acoustic wave gets reflected and comes back, and it behaves almost as if a open as if a acoustically closed end. It's very close to it, and that brings us to the concept of acoustic impedance. Thank you for the question, and we will get to that. But before that, I want to give a homework or classwork. Can you try to derive the natural frequency of a tube which is open and open? You can do it now. So for an open condition, P equal to P prime is P minus P bar, which is P bar minus P bar equal to 0. So you can say P hat of 0 is 0 and P hat of L is 0. So what would be the natural frequency you get? A decay tube, for example, will work very close to an open end. Yeah? N. So in this, so we saw that the closed open end, that kind of tube was called quarter wavelength. So open and close, they are like half wave tubes. So I wish to emphasize that for any solution to any ordinary differential equation, you need boundary conditions. So the type of boundary conditions we used are in terms of pressure equal to 0 or dP by dx is 0. So these are called Dirichlet and Neumann boundary conditions. We also can have a mixed boundary conditions of the form P prime plus let's say alpha times U prime equal to 0. So this would be a mixed boundary condition. So this would mean that alpha would be equal to minus P prime by U prime. So we can rewrite alpha with minus Z and we can say Z equal to P prime over U prime. So this Z is called impedance. So for a general boundary condition, this is what you would be using, and we will see later that the either if you have pressure as 0, P prime as 0 or U prime as 0, then you do not do any work at the boundaries. If you have either P prime as 0 or U prime as 0, the quantity P prime U prime, which is like the work done or the acoustic intensity, would be 0 at the boundaries. So that means no work is done or taken out, and therefore if you have a measure of the acoustic energy in it, and it would stay as constant, but in reality it could be possible that the energy is radiated out of the duct or coming into a duct, and then you would need such a boundary condition. So this quantity P hat over U hat is called Z, and then in general it is a function of frequency, and this is called specific acoustic impedance. And it is written at the interface. So in case you are talking about some interface, this is the if the velocity is not one dimensional, then this actually amounts to the velocity which is normal to the interface. And in general frequencies of different waves of different frequencies behave differently at the interface, so which is why this coefficient is Z is a function of omega. And I wish to emphasize that this is different from the characteristic impedance. Characteristic impedance is a characteristic of a medium, and there it is defined as rho c, and that's a property of the medium, but this actually depends on how the waves behave. The waves may be getting reflected at some boundary and coming back and so on, and therefore you can have pressure going as F plus g, but velocity may be like F minus g, and so it depends on the boundary values. How the reflection takes place at the boundaries and so on will affect what the impedance value is, whereas the specific acoustic impedance does not really it depends the characteristic impedance of the media does not depend on the geometry or any such thing, it just depends on the fluid, whereas here this can depend on a lot of things. Now you can so this is like in electricity we have impedance, which is the ratio of voltage to current. So this is very analogous to that, and I think this kind of approaches came from electrical engineering, and we can non-dimensionalize it as so this would be the zeta of omega would be the non-dimensional impedance, and rho c is the characteristic impedance. We can also define a quantity called admittance, which is U hat over P hat. So this is like the reciprocal of impedance. So admittance is usually given by the symbol Y, which goes like 1 over Z, and this is similar to conductance. So current divided by voltage is conductance, and admittance is indeed a very physical quantity. You can actually express the energy that is coming in or the acoustic intensity that is coming into a tube or going out of a tube in terms of the acoustic admittance, and we will see that later. So we need this to quantify what is the acoustic power that is coming into a medium or going out of a medium. So if we had nice boundaries like velocity 0 or pressure 0, then I mentioned already that the acoustic energy in the tube will stay constant, but if you have something coming in or going out. Let us say there is acoustic power coming into the tube, then what happens to the acoustic energy? It will keep growing. So there will be kind of growth rate. Of course in linear theory it will keep on going exponentially to infinity, but in reality non-linearities will come in and this growth may not happen forever. But let us say we have a growth and we have to determine the growth rate, and this growth rate can be determined in terms of the impedance or the admittance. Similarly, if you have acoustic energy in a duct and the energy is going out of the duct, then your acoustic field will decay, and the decay rate can be expressed in terms of the impedance or the admittance. We will do that in the coming classes. We also need to have a measure of the acoustic energy, so we can write the equations in a dynamical system language as now I have written in this manner so that this operator gets normal and then it becomes a nice form. If I do not normalize by rho c, then I would not have this operator here being normal, and having a normal operator has a lot of good properties. So now if this is the state variables, so you have state variables as u prime and p prime over rho c transpose. So you need some kind of measure for the some kind of measure characterizing the system, or the norm which characterizes the energy of the system, and so that can be obtained by squaring this and squaring this. So it will go something like u squared plus p squared, except there is factors in front of these things. So we will see if we can get such a measure of acoustic energy of the form of velocity squared plus pressure squared weighed appropriately. So the velocity squared would correspond to the kinetic energy associated with the wave, the pressure squared will correspond to the compression and rarefaction energy in the wave. It is like a spring, when it is compressed it has some energy stored in the spring, so pressure squared would be some term of that sort. So we will do this in next class. So in summary, we have taken a quick look at standing waves in a duct, and we have now know how to calculate the natural frequencies of ducts which are open and with open ends and closed ends, and we even thought of how this can be used to calculate quick estimates of natural frequencies of even such a complex thing as solid rocket motors, and then we ended with the definition of impedance and admittance, and we will see how that can be used to characterize the growth and decay of acoustic energy in the systems. I will stop here, see you tomorrow, have a good day.